Okay, this is going to be part 2 of the video series that involves the integrals of the 6 basic trig functions. Now, in the first video, in part 1, we derived these 4 integrals here involving natural log, and we showed where the formulas came from. Now, in this video, what we'll do is show how to actually use these in some specific example problems. And we'll show some of the variations, like some of the problems will require U-substitution, some of them will require trig identities. There's lots of variations in these. So let's look at a few examples and see how to use them. Now again, the 6 trig derivatives are here on the left, the 6 basic trig integrals are here on the right. So let's look at a couple of problems. Now the first thing that pops up is this: how do you know when to use U-substitution or not? And the answer is just what it's been throughout the entire calculus course so far. If you're finding the integral of just a simple x, then you do not need to use U-substitution. However, if it's anything more complicated than a simple x, then you will have to use U-substitution. So the problem on the left, we won't have to use it. The problem on the right, we will have to use it. So let's go ahead and get both these answers. So first of all, what this one's going to be, it just says, what is the antiderivative of the tangent of x? And all you really need to do in this one is just go back to your formulas. So the formula says this: the antiderivative of the tangent is the negative of the natural log of the cosine. And that's going to be the answer. So this will just turn into the negative of the natural log of the absolute value of the cosine of x plus c, and you're done. There's the answer right there. That one did not require U-substitution. But on this one over here, now you've got something more complicated than just a simple x in here, so you are going to have to use U-substitution. So on this problem, we'll do the following. We'll let u be equal to what's inside the parentheses here. So we'll start by doing a U-substitution. So u will be equal to 3x. Then find the derivative, just typical U-substitution. The derivative of u with respect to x would be equal to 3, which means that du would be equal to 3 dx. Now again, in U-substitution, we're trying to change it from an x problem into a u problem. So there's a dx. I've got 3 dx here. I need to get rid of this 3. I'll move it to the other side, which gives me 1/3 du would be equal to dx. So there's my substitution right there. This dx here matches up with this dx here, and I'll substitute that part right there for it. Again, I like to put a little box around these just to isolate this U-substitution. So we'll do that here. We'll go from here and just stick this thing in a little box just to isolate it. So this was the U-substitution. Okay, now that you've got that, we'll go back to the problem and stick it in the problem. So this then will change into the tangent of, and in place of 3x, put what 3x is equal to, which would be u. So this will be the tangent of u. And in place of dx, put what dx is equal to, which would be 1/3 du. So I've got a 1/3 du there. Now it's just a matter of solving this. And the first thing, the 1/3 is a constant, so you can go ahead and bring it to the outside of the integral. So this would be 1/3 the integral of the tangent of u du. Okay, so that's going to give you 1/3, and now we'll go ahead and find this antiderivative. So looking back at the rules, the integral of the tangent, again, is equal to the natural log of the cosine. So it's going to have the same form as what it had over here. So it's going to be the negative of the natural log, the absolute value of the cosine of u, and then you've got a plus c over here. And you're almost finished. The last step would be to replace u with what it's equal to, which is 3x. So in this problem, in the final answer, we'll bring the negative out in front. So negative 1/3 the natural log of the absolute value of the cosine. And again, in place of u, put what u is equal to, which would be 3x. Then tack on a plus c to account for the constant, and you've got it. So that's what the solution to this problem would look like. So just remember, if it's a simple x, you do not need to use U-substitution. If it's something more complicated than a simple x, then you do need to use U-substitution. So you let that be your guide as you go through these. Okay, next problem. This will be actually the same thing. We're just going to show one more example using U-substitution on this. And again, we work with a cosecant one this time. But again, this is more complicated than just a simple x. So I'll let u be equal to what's inside the parentheses here, and we'll take care of the U-substitution first. So that means that u would be equal to 4x plus 2. Then find the derivative. So the derivative of u with respect to x would be equal to 4, which means that du would be equal to 4 dx. Now again, look back up at your problem. You're going to try to change this into a du, and here's the dx, but you've got a 4, so move the 4 to the other side, which gives you 1/4 du would be equal to dx. So now this dx matches up with this, and this is going to become your U-substitution right there. And again, we'll stick a little box around this just to isolate this. So keep the U-substitution all by itself. So there is the U-substitution right there. Okay, now what that does to the problem then, this will turn into the integral of the cosecant, and in place of 4x plus 2, we'll put a u, and then finally in place of dx, we'll put what dx is equal to, which would be 1/4 du. And now just treat it like any other U-substitution problem. Bring the 1/4 out in front, so that will be 1/4 of the integral of the cosecant of u du. Okay, so that gives you, here's a 1/4, and we'll put some brackets right here. Now just look at your integral list and find the integral of the cosecant. So going to our formula list, the integral of the cosecant is the negative, the natural log of the cosecant plus the cotangent. So let's go ahead and use that. So it's going to be the negative of the natural log of the absolute value of the cosecant of u plus the cotangent of u. And then tack on a plus c to account for a possible constant. Okay, you're almost finished. The last step now is just to replace u with what it's equal to. And I think I'll go ahead and put this negative out in front again. So a negative 1/4. Then I've got the natural log, absolute value of, here's the cosecant. But in place of u, put what it's equal to. So you've got a 4x plus 2 right here. And you've got plus the cotangent. And again, replace the u with a 4x plus 2. Absolute value sign plus c, and you've got it. So that's just one more example showing a cosecant, but again, it required U-substitution because you had something more complicated than just a simple x right here. Okay, let's try another example. Now this one's a little different because sometimes you'll run across problems that require identities. And when you first look at this, if you try to match it up with something in your list, you've got 1 plus a tangent squared and you've got a secant. But if you look at your list of rules, there's nothing over here that matches up with that. So if that's the case, you have to begin to work with it to try to turn it into something in this list if you can. So what we'll have here is this, I've got 1 plus the tangent squared. You can't divide, you can't cancel anything out. So if that's the case, think about identities. Now in this case, you might remember from your identities that 1 plus the tangent squared is equal to the secant squared. So I'll take advantage of that rule and I'll change it into this. This will become the antiderivative of, and again, 1 plus the tangent squared is the secant squared. So this will change into a secant squared, and then divided by the secant down here, all dx. Now what that does is this, you've got a secant on the bottom, and you've got a secant squared on the top. So the secant on the bottom cancels out one of the secants on the top, which leaves you with an integral of the secant of x dx. Now, as you go through it, continue to look back at your list and see if you've got it to something that you can work with. So now we've got an integral of secant. Go back to the list, and here is the integral of secant. So the integral of secant is the natural log of the secant plus the tangent. So now you've got something you can turn it into. So this will turn into the natural log of the absolute value of the secant of x plus the tangent of x, tack on a plus c, and you are done. So the trick on this one is just keep an eye out. On some of these problems, you can use identities. So if you find yourself stuck, you're not sure what to do, one of the things to check for is, will an identity work to turn it into something that you can actually use? Okay, let's take a look at the next example. Okay, now in this next example, let's try some things at first. You might try an identity again. Remember, identities worked on the last one. But what you'll find is that the cosecant and the cosecant times the cotangent, there's no identity that actually works here. And some students always try to do this. They'll say, well, let's just cancel out the cosecants, but you can't do that because this has a cosecant plus 2 on the bottom. So the little trick on this one now is to think again about U-substitution, and this will actually turn into a 1 over U problem. And watch how this works. So what I'm going to do is this. I'll make this, rewrite this as the integral of, and put the bar across here. What I'm going to do is take this. I'll take this cosecant cotangent and just scoot it off to the side over here, which will leave me with 1 over the cosecant of x plus 2, and then over here I'm going to have the cosecant of x times the cotangent of x, all, and then dx. Now, why would you want to do that? Well, you need to look back at your rules and say, again, under U-substitution, the idea is pick your U so that its derivative gets rid of the other thing. Well, if I let U be equal to the cosecant of x, and again, let's look at our rules, the derivative of the cosecant gives you cosecant cotangent, and you can use that to eliminate that term. So, and actually it's the negative of the cosecant cotangent, but let's run through and see how we use that then. So what I'll do is I'll do a U-substitution and watch what happens on this problem. So I'm going to go ahead and let U be equal to this right here. There's my choice of U. So we'll do the U-substitution over here. So let U be equal to the cosecant of x plus 2. Then you want to find the derivative of U with respect to x. And if you need to, look back at your list of rules. So again, the derivative of the cosecant is the negative cosecant cotangent. So this will turn into negative cosecant cotangent. And the derivative of 2 is 0. So you can put a plus 0 out here if you want to. Okay, now that means that the differential of U would be equal to the negative cosecant cotangent, and then dx right here. Now, what I'm trying to get rid of in my U-substitution is this right here. So I'm trying to eliminate this using U-substitution. And sure enough, here it is. The only trouble is this negative. I don't need the negative, so move the negative to the other side. So that gets you to a negative du is cosecant x cotangent x plus dx. So now this matches up with this. So here is your U-substitution right here. You'll substitute this part right here. And like always, we'll stick this in a little box just to isolate it here. So we'll go, this will keep the U-substitution separate from the rest of the problem. So there was the U-substitution right there. So now let's see what that does to the problem. So now this will turn into this. It will turn into the integral of 1 over U, and all of this turns into a negative du. So we'll bring the negative out in front, so it'll be the negative of the integral of 1 over U du. Now, before we go on, take a look at the problem. What happens? So occasionally you'll get this. You'll start out with the integral of a trig problem, and in the process of manipulating the u's, it will turn into a non-trig problem. So this thing turned into a problem that doesn't even have a u on it. Now, just a reminder, the integral of 1 over u, and using your formula, is this. So the integral of 1 over u is equal to the natural log of the absolute value of u plus c. So we'll take advantage of that in this problem. Okay, so this will turn into the negative, and again, this turns into the natural log of the absolute value of u plus c, using that definition. And then your final step, again, is just to go ahead and replace u with what it's equal to, which would be the cosecant of x plus 2, and then tack on a plus c out here at the end. So there's going to be the answer. Anyway, just be aware of the fact that sometimes you'll do this. You'll start out with the integral of a problem that has trig functions in it, but in the process of manipulating it, it will turn into a non-trig problem. Then you find the antiderivative, and at the very end of the problem, just substitute u with what it's equal to. Okay, one last example. Okay, now occasionally you'll need to do this. You've got a cotangent plus a sine. Now, whenever you have a plus or a minus, consider splitting the integrals. So just a little note to yourself, just another option on these problems, split the thing if you can split it up into integrals. So what we'll do is split this up into this. We'll make it be the integral of the cotangent of x dx, and then plus the integral of the sine of x dx. So as long as you have a plus or minus, you can split it up into two separate integrals. Now each one of these has their own definition. So the integral of the cotangent, again, go back to the list, and the integral of the cotangent is the natural log of the sine. So this will turn into the natural log of the absolute value of the sine of x. And there's a plus c, but we'll save that for the end. Then plus, now the integral of sine, let's go back and look at the rules. The integral of sine is the negative of the cosine. So this is going to become, you'll have the negative of the cosine of x. And then finally, you've got a plus c out here on the end. Now, if you want to, you can take this negative and move it out in front, so the final answer would look like this. The natural log of the sine of x, then you'd have minus the cosine of x, and then finally a plus c to account for any constant. So it looks like that. So in each of these problems, you saw some variations. Some of them required trig identities. Some of them required U-substitution. Some of them required splitting the integral. Sometimes the problem changed from a trig problem into a 1 over u problem. So as you work these out, just be aware there's lots of variations, but they all are based on this set of integrals right here. So at some point, you've got to try to turn it into something that will agree with one of the integrals in this list.